a little bit not very kind, so to say. So yesterday we noticed in the participants' presentation that the auditorium was way less crowded than during the rest of the day. Just a very, very kind and friendly reminder that assisting to all the events in the school is equally important, especially because, well, I don't think I should be saying this, but the slot that you have is competitive, right? There were like, if we have 100 people here, there were about 300 people that wanted to come, and you're one of those. So I think that at least for a matter of responsibility, education, and all these things, we should all stay here until the end, especially those that have fellowships that cover absolutely all the expenses that you have here during the week. Second announcement, we have a little modification in the schedule today. We will start at 2:15 instead of 2:30. So that, together with afternoon seminars being a little bit shorter, we're going to try to finish early. So if you put a little bit on your side to stay until the end, we modify a little bit the schedule. Let's see if we keep all together until the end of the day, right? And this being said, I'm as happy, or a bit more happy than yesterday, to introduce Stefan Alexina, who is going to continue with his course on the Generalized Lotka-Volterra Model. Thank you.
All right, thank you. Good morning. So I thought that yesterday we covered a lot of ground, so that we would have a little recap before we move on with more Lotka-Volterra. So just like previously on a tour of the generalized Lotka-Volterra model, we've seen a few things. First, we saw the generalized linear Lotka-Volterra model that we need, which is like this model here, diagonal of x, growth rates, interaction with the other species. And then we saw the definition of an equilibrium. So imagine that this matrix is not singular. Then we can solve a linear system, AX is equal to minus R, which we can do by inverting the matrix A. Multiplying by the vector of growth rate, we get a vector here. We call that x star. And we define these to be feasible, meaning can be achieved by a natural community if it is all positive, right? Because these are densities of species, the x. Importantly, we saw that in the generalized Lotka-Volterra model, this feasibility of an equilibrium is needed for coexistence. Even when coexistence is not at an equilibrium, right? Even when we have limit cycles or chaotic attractors or whatever you want. Then we went on a tangent on the local stability of this point x star, right? So imagine that this equilibrium exists, it's positive, it's feasible. Then we can ask, what happens if I just slightly perturb it? Will the system go back to the equilibrium, meaning it's attractive at least locally, or will it go somewhere else, meaning it's not attractive, unstable? And we saw that to do that in Lotka-Volterra, it's very easy because all you need to do is to check the eigenvalues of a matrix that we call the community matrix. We saw this is the Jacobian of the system evaluated at a fixed point x star. And in the Lotka-Volterra case, it's the easiest form, so it's just a diagonal of x star times the matrix of interactions, right? So if this matrix is stable, meaning all its eigenvalues have negative real part, we say that x star is locally asymptotically stable, right? Meaning slight perturbation goes back to the equilibrium. Then we said, can we say something stronger? And I told you it's typically difficult to say something stronger, but there are certain cases where you can. And especially if this equilibrium exists and it's positive, and there exists a matrix C diagonal with all positive components on the diagonal, such that the symmetric part of A, when it's multiplied by C, is negative definite, meaning has all negative eigenvalues. And these eigenvalues will be real because this is a symmetric matrix. Then x star is globally attractive, meaning I start all these species in the community at any point that is positive, right? I cannot start them at 0 or negative, but if I start them at positive numbers, it will go to x star. So this is what we said about the model itself, and then we started thinking about large communities, like large community composed of n species, where n you can take to be a large number, you can choose the large number that you like the best, in which species interact with each other with a certain probability C, right? And when they do interact, we sample their interactions from some distribution, right? A random distribution. And we talked about the case that is the simplest of like mean 0 and variance sigma square for this distribution. And then imagine that we put something special. I'm kind of have a little bit of feedback. We put something special on the diagonal, a constant d. And as I told you yesterday, this constant diagonal will set the mean of the eigenvalues, so like the center of the distribution of the eigenvalues in the real axis. And then we went through showing that using very basic results from a random matrix theory, you can derive this inequality, which is the famous like May stability criterion. And then that using a slightly more involved formulation that involves like sampling the interactions in pairs instead of one at a time, we can extend this to the case in which these interactions between species are correlated, right? And this is the work that I've done with C-Tang in 2012. One thing that I forgot to mention, which is in fact the whole point of this study of May and then of myself, is why is this interesting? And this is interesting because imagine that we're fixing D, C, and sigma square. And then we start cranking up n, right? So because this is a function of n that grows with n, eventually we will cross this stability, right? So like if we have a system and then we start just adding more and more species without changing the rules in which we build the system, eventually we will cross this point of stability, right? So a large community, large enough, you can make it unstable, right? And this was the whole point that made like May work controversial. It should not be controversial, but that went on for about at least 40 years. All right, so this was the recap of the previous episode. And today, what I would like to do is to talk about something that actually was mentioned by Priyanka yesterday, which is good because like we absolutely did not coordinate, and yet, you know, we're having a very complementary set of lectures. And especially, I would like to take this system of Lotka-Volterra and then start building, for example, community from the ground up, right? That's what we would call like ecological assembly or succession, and then have some sort of focus on invisibility, which you've seen yesterday, a lot of invisibility to say, can this predator invade when rare? Can the other consumer, blah, 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 that kind of thing, but a little bit more in general. And just like before we get into the thick of it, I want to just show you like what is that I have in mind in terms of process. And then I want to list a few things that could go wrong. And then I'm just going to ignore all the things that can go wrong, and we will study a case where all these things don't go wrong so that we can do some math, right? But just like to raise awareness that this is indeed a difficult problem. So what I have is like, the simplest case would be that of a mainland. Imagine that I have some sort of like continent and there's all these species. And then I have an island, right? And initially there's no species. This is a volcanic island that came out yesterday, right? So there's nothing there. And now, little, by accident, you know, some species will get into the island, right? So imagine that the species E will get into the island. And then, if it can survive on the bare island, for example, it's some sort of like, I don't know, moss or whatever else, it could establish. If it's a lion, it will die, right? It will fail to evade. And then, you know, maybe it establishes, and so now we have E on the island. And then, after some other time, maybe another species comes in, like F. And what can happen then? It could attach to the community, right? Now we have E and F on the island, or it could go extinct, so we still have only E, or it could displace E, so now we have only F, right? So this process, and you can imagine, we can keep going. And what we're going to study mostly is like the asymptotic regime, like what will happen at the end of times, right? Like if we were to wait for long enough, where all the things that could happen have happened multiple times, what happens then? All right? So this is like the process of assembly, or you could think like it was very popular in the first part of the 20th century, the idea of succession. Actually, that was pioneered by Coles, that was where at the University of Chicago, and wrote this famous paper on the sand dunes in 1901. Right. But now, you know, like this, I swept a lot of details under the rug. And these details turned out to be very important, right? For example, how often do species come in? You can imagine like that when we're doing, I don't know, population genetics, how often are mutations coming in? They're very rare, right? Because we don't like to write more than 2 equations. So we say there's a wild type and there's a mutant. There's only one mutant. If we wanted to do population genetics with high mutation rate, we would have to rewrite completely population genetics, right? So that is like one thing that is interesting is the time scale at which species come in compared to what? To the time scales of the dynamics. And what I mean by the time scale of the dynamics is, imagine that this species F is coming in and it's sending E to extinction, right? How long does it take for E to go extinct? And so if I have another invasion during this period in which E goes extinct, I'm basically in a situation where I have 3 species. If instead the extinction rate of E is much faster than the next invasion, then I will always have like 1 species coming in at a time. Right, so this you could think of a time scale, or you could think of a size of the invasion. Does only 1 species come at a time, 2 species come at a time, 3 species come at a time? And if invasions were fast enough, we could say all the species come in at a time, right? Which is like the other end of the spectrum of things that can happen. So that's one thing, is like timing or the size of invasion. The second thing that I didn't mention, which is important, is what about the density of the invader, right? Does it come in with a few individuals, with very many individuals? What does it do? And you can imagine, imagine that I have like the typical like bistable Lotka-Volterra system of competition, right? If I come in like species A is established, and then I come in with very low abundance, I go extinct. But if I were to come in with a sufficiently large abundance to move in the other, at the other side of the separatrix, I would win this competition, right? So that is like the other problem, like the density of the invader. And then more complicated still is what about, we're thinking this world where everything is frozen, right? All these states are equilibria, right? But what if the species were cyclic or were in a chaotic attractor? Then if I come in at the right time, maybe I can invade. If I come in the wrong time, maybe I cannot invade. So what happens there, right? So this is like the problem of these attractors. Or dynamics or something like that. I don't like this fact that maybe we can turn this on like a little lower. Right, so these are all things that can go wrong. And actually, they're very, very difficult to deal with mathematically. And so if you look at the literature on this ecological assembly, you will find that like starting in the late 1980s, early 1990s, and then it went on for about 10 years, people got really excited because now we had these machines, right, this piece of plastic that can do all these calculations for us, and now we're going to solve the problem of ecological assembly. It turned out we did not, right? So it's a sad story, but it's the way it is, right? And so, like, I feel that these machines are very, very powerful, but they're all useful if you know what you want to look for, right? And so if we don't have a basic understanding of this process, we can simulate the crap out of it, but then we would not know what to look for. And so we need to have some sort of guidance and understanding. And typically, this comes from what? From looking at simplified cases, right, in which we can remove some of these difficulties, and then maybe we can get an understanding of what is the null case, what should we even expect from such a process. And that's exactly what I want to do today. So how do we get rid of all these problems? First, let's get rid of the problem of the time scale. So we assume, for no good reason, but that's what we're going to do, that invasions are rare, right? So that the time between invasion is long enough that whatever dynamics could have happened in between happened. This, as if, I don't know if it's a bit subtle, but it's a huge assumption. Because of what? Because the time it takes for things to happen in the system depends on who's in the system and what kind of conditions are there. So imagine that I invade with two species, I invade one species, and then another species comes in that would displace the rest of the species, but they're very, very, very similar. What would be the time to extinction? It would be very long, right? While if a clearly superior competitor comes in, it will displace it immediately, right? So by doing this assumption, we're basically saying species come in very, 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 very slowly, all right? So spaced in time, these are our solutions, like, or tricks, or like simplifications. Then let's get rid of the problem of the density of the invader. So what I'm going to do is exactly the same that we do for population genetics or other things. I'm going to assume it is very, very small density, right? So there are only a few individuals came in, such that they do not really influence the resident community as much, initially at least, and they don't feel their own population as much, right? So that we don't have to care about self-regulation and whatnot. And then this is like the elephant in the room. How do we get rid of that, right? That is hard. And so what I'm going to do today, you can do something slightly more general, but like for simplicity today, what I'm going to consider is like symmetric matrices, right? Under symmetric matrices, what we have is what? That any symmetric matrix that is stable abides by this rule, right? Because you can just multiply by the identity matrix, for example, and that would be true. And as such, if an equilibrium exists, it's globally stable, which means I only have to deal with equilibria. I don't have to deal with limit cycles. I don't have to deal with chaos. I don't have to deal with anything like that. Okay, so this is like these are all strong assumptions. I would not recommend doing this at home, but you know, like that's what we need to do to get a result. All right. So with this at end, let's think of this process of the first species coming in. So we have like the bare ground, like the new volcanic island. And what we want to do is to see whether the first invader can establish or not, right? And as Priyanka did yesterday in her lecture, what we want to really see is like that initially it can grow, right? And then if it can grow initially, because of these assumptions that we made, it will go to its own steady state, its own equilibrium. Right, so if we write the equation, and we write the equation for like the per capita growth rate, and so this is species A1, and then it will have a growth rate R1 plus A11 X1, right? So this would be my equation. But then because I say it's very low abundance, this initially at least is 0, right? Or very close to 0, so that I don't care. So that then the criterion for invisibility of the bare ground is very simple. If you can grow there, you will grow there, right? So if your growth rate is positive in this environment where you're introduced, then you will grow there. Now, let's think of the second species that comes in, right? Now imagine that the first species went to its own equilibrium, X1 star, and now a second species comes in. So if I write like this equation for species 2, so I would have what? Like R2, right? The growth rate of the second species plus the sum over J of A2J xj, right? But who is J? There's only two species, right? There's the resident species, X1, and then there's the new species, X2, which is basically 0. So what I'm going to just do is to simplify this and just say A21, X1 star. Right? So can it grow when the other species is at its carrying capacity, basically, which is exactly what Priyanka did yesterday, right? And so this gives me a criterion for invisibility of the second species, which would be this thing has to be positive, right? So I have to have R2 plus A21 X1 star has to be greater than 0 for this species to grow. All right, so we will call of this type of inequalities like an invasion criterion, and we can write it more and more complicated ones. At some point I will stop because it gets too complicated. And, yes, oh, there's a question, yes. Okay, so sorry, maybe I did not explain myself properly. So this species, if it can grow, it will grow to what? It will grow to its own carrying capacity, right? X1 star. Right? So imagine that now this island is completely covered in moss, and now this other species comes in. Can it grow in an island that is completely covered by moss? That is the question, right? So that's why this is at its own carrying capacity, because it does not feel the new invader yet because it's very low, and the invader does not feel itself, so we can get rid of that term, and that's how we do it. All right, as I was saying before, like when we're introducing, imagine that this is the case, that we have somebody that initially can grow, what can happen? So there are very many things that could happen. For example, it could grow initially and then go extinct. Turns out that under these conditions that I gave you, that cannot happen. So if you start growing, you will grow. We will keep growing, and you will be part of the final community no matter what. Or another thing that can happen is it starts growing and it displaces the resident species. So now we're back to square one, like with only one species, but now we have only species 2 instead of having species 1. Or it can coexist with species 1, right? In which case we will get a new equilibrium that contains species 1 and species 2, okay? Now we can think to reiterate this process over and over and over and over until we build like a community, right? And this is what we call this ecological assembly. Now let's try to do this a little more generally for instead of having, because like we could start with 1 and then do with 2 and do with 3 and but you can imagine it's the same thing. So we're just going to write this for n species. And so the way I'm going to do this is like I always think there's a pool of species. These are like the species in the meta communities, imagine like in the mainland. And there's n species. And then there are like resident species that are coexisting. And I call this K, right? K for coexisting with a K. All right, so at any point in time, right, I have that these species, as we were saying, they go to some equilibrium, right? X star that has K components, and then the other species are absent. So this is also a solution of this equation. It's just that it's not a feasible equilibrium per se. So to call this, I will call this X bar as opposed to X star. And X bar has like 2 components, which I'm going to order such that at the top we always have the resident species, and at the bottom we always have the species that are absent that could potentially invade the community. So sorry for the notation that it's a little. So this X of K would be the equilibrium for the K species by themselves, okay? And then we have a vector of zeros here of length n minus K. Okay, so these, you can imagine like I have my species 1, 2, and 3, and I don't have 4, 5, and 6, so it would be the equilibrium for species 1, 2, and 3 at the top, and then 0, 0, 0, right? This is my vector. And similarly, I can write the growth rates for the system, again, as R for the resident species, R for the invaders, or like the species that are absent. And then I can partition my matrix of interaction to have like a block structure, right? So I will write this as 4 blocks of a matrix. There's an A, K, K matrix. This is the matrix of interaction between the resident species, right? So you can imagine taking out of like the general matrix just this slice that has only the rows and columns pertaining to the species that are in the community. And then I have another matrix that I call A of K n minus K, which would be the interactions between the resident, like how the non-resident species would influence the growth rate of the resident species. I have another block here, which is the opposite, how the resident species would influence the growth rate of the species that are absent, n minus K, K. And finally, I have, like, to complete this matrix, I have n minus K here which is like the square matrix of the interaction between the species that are not there. All right? Is this clear enough? So we can always divide these. We can rearrange the rows and columns of these things however we like, and we like it in the way that at the top we have the resident species, at the bottom we have the rest. Okay, so how do we write? This has to be some sort of feasible equilibrium point. Right, so what we want to know is whether x of k, which we can always write as minus a k inverse r of k, this has to be greater than 0. So this is the feasibility of the resident species. And what we would like to do is to determine whether this equilibrium x bar is the final equilibrium that we can find, right? So that if we keep adding species, they cannot invade, right? So if we have a pool of species and we have an equilibrium such that the resident species are coexisting happily with each other at a stable fixed point, and all the other species cannot invade when rare, we call this a saturated equilibrium, right? So it's a special equilibrium in the sense that some of the components are 0, but those that are 0 cannot invade, and those that are non-zero are living happily with each other. So to write a criterion for non-invasibility, we have what? We have a generalization of this thing here. And you can think like the growth rate of the non-resident species when they feel the influence, which is coded in this a n minus k species, right, that are resident and they're sitting at xk, lower than 0, non-invasibility. Right, so what is a saturated equilibrium point? K species are there, are feasible, stable, the rest cannot invade. This is what we call a saturated point. And what we can do is to do something similar to what we've been doing here to show that if a saturated, like for each one of these systems actually that we're going to see, there is a unique saturated equilibrium point. And this is globally attractive, meaning like that if we start the system however we want with all positive species, it will go to this point, right? So some species will go extinct and the other one will sit at xk, whatever that is. To do that, we do exactly as yesterday. We write a Lyapunov function. So just to clarify, because I think in the questions I kind of sensed that not everybody understood exactly what we were saying with these Lyapunov functions. So the idea is we want to write a function that describes the system, some summary statistics of the system, in fact. Right? And we would like this function to change in time, right? Like, so we typically write a differential equation for this quantity. And what we would like to do is to have a function that takes a value, a special value of 0, only in the point that we want to show to be globally attractive, in this case x bar, and it is decreasing everywhere else in the positive orthant. If that's the case, you can imagine I start wherever I want and I start decreasing, and I start decreasing, I decrease, and eventually I reach 0. And that means that for wherever we start, we always end up in the same place. Is this clear? Because we're going to see more of this also tomorrow. Okay, and as I told you, finding the right function to write is not trivial, right? So these, I think I got from Hofbauer and Sigmund, who are very good at doing this type of thing, in 1998. So you find in section 15.3 of their book that is cited in the notes. So what we're going to do is we're going to write v of x is minus the sum over I of ci, and then x bar log of x minus, let's do it in component form, minus xi. So the ci is basically the same form that we had before. And notice one little thing. 0 log 0 is 0 in this derivation. Just because otherwise, what do you do with that? Okay, so then we can take derivatives with respect of time of these, right? And what is time varying is really the x, not the x bar, right? The x bar is some sort of number that we want to show it goes there. And so if we do that, we write the v x dt is minus the sum over I of ci and then xi and then d log xi dt, which if you remember is what? This we derived yesterday, right? What is the equation for d log x dt? It's just r plus ax, right? If you remember from yesterday. And then minus dxi dt, which is the Lotka-Volterra function. And so this we can substitute here. We put this whole thing is just r plus ax. This whole thing is diagonal of x, r plus ax. So you can see that this is exactly the same thing, right? Here we're multiplying by xi bar, here we're multiplying by x, so we gather these terms. And so we can write minus sum over I of ci of xi bar minus x, I, and then times our Lotka-Volterra thing like sum over j of aij xj. Good. So now, what I would like to do is to write this sum. Maybe this is a little too involved, but it's early, so we can do this, right? So I want to write this sum as the sum of two sums, right? I want to write this as aij, and then here I put xj minus xj bar. So I took out xj bar from the sum, and then I sum it again, right? Sum of aij xj bar, right? And why do I want to do this? Because then these terms looks very, very close to that, right? So if I do this. So sum over I of ci, and then I have x bar I minus x I. And then what I'm going to do is to say, well, look at this. Now I have this piece here. I flipped its sign, right, so that I get exactly the same as I have here. And so then I can write sum over I and j of ci. And then here I'm going to put aij. And then I have the same thing again. X bar j minus xj. Okay, and if you think, you can put the ci here if you like. So if these metrics were to be negative definite, right, and this is like saying a negative metric, definite matrix, we were saying yesterday, like we have always is lower than 0 for any choice of y in Rn. So this is a choice of y in Rn. So this is going to be what? Negative. Right? And here I got rid of this minus by switching the signs. And so this part is always negative, which is good, right? Because that's the direction we would like it to go. But now we're left with another part that is this other part here, that now we have to say minus the sum over ICI of xi bar minus xi times the Ri plus sum over j of aij xj, which is what? So this, you've seen it before. In fact, you've seen it exactly here, right? This is the Bayesian criteria. So if we have an equilibrium for which, you know, like these conditions hold, that this is feasible, stable, and this is non-invasible, then this Lyapunov function will be defined to be always negative, and therefore it will always go there. Yes? Questions on this? Yes?
I have a question. In that process, you say that we will add a new population after the population before reaches the fixed point, right? So what happened with the first case where there is no fixed point?
There is a fixed point, which is like the empty island, right? There's nothing there, right? That you could consider also as a fixed point. All right, but like just to make like this summary of this part, for any pool of n species, there's going to be some vector, which we call the saturated equilibrium, in which a certain number of species, which we call k, and we smartly rearrange all the coefficients such that they're at the top, will be there at some positive numbers, and all the other species cannot invade. Right? All right. So armed with these results, we would like to ask, how big is this set of species that coexist? If I give you a pool of species. Yes?
This is a kind of potential analysis that we're making, right? I want to know from where does this explicit form come back? It's a kind of tricky potential, right?
This Lyapunov function?
Yes.
I did not dream this up myself. I wouldn't know where to start, actually. Like, so that's why I'm saying that this is non-trivial. Like, there are some sort of rules of thumbs for deriving these Lyapunov functions, but it's not a science. It's more of an art than that. All right, but like, you know, yesterday we were saying, oh, look, like if I take a system that is large enough, it will be unstable. And what happens then? Does it burst into flames and then there's like the bare ground again? Does it like go to one single species or not? I'm not much of a biologist myself, but you know, if I go around, there's a bunch of species almost everywhere. In fact, it's so difficult to keep only one species. If you're a good American, you want to have like a nice lawn with a single species there, it's hard, right? So what's so hard about coexistence, right? We're always talking about coexistence. This should be the most natural thing ever, right? And instead, we're writing papers and papers on how to keep like this thing from having a single species of grass. All right, so how many species will coexist? Right, so as I said, for simplicity, we take to be this matrix A for the whole pool, right? So the n times n matrix to be stable and symmetric. And therefore, it's Lyapunov diagonally stable with random coefficients, right? So it's a random matrix that is symmetric and it's stable. And then we take like some sort of vector of growth rates, which is also random, right? So imagine you sample this from a normal distribution. And this actually turns out to be very nice. So we're saying A is a random matrix, is stable and symmetric. And then R is like a sample from a multivariate normal distribution with mean 0 and whatever variance you like, sigma squared. Okay? And I want to derive how many species are at the end if we parameterize the system like that. So this is non-trivial, but there is a trivial case which is very simple, which is to say, what if A were to be a diagonal matrix with a negative diagonal, right? So species do not care about each other in the least. Then can you tell me how many species will coexist? Right, so it turns out like if I can grow in this environment, I will, and I reach my carrying capacity. And if I sample these from a normal distribution centered at 0, or any distribution centered at 0, how much will that be? Like 50% chance, right? So I flip a fair coin and decide whether this species can be there or not. And then if I start this process and I have n species, what is the distribution of the number of species I would see? It's the distribution of the number of heads when you flip n coins, right? Which is called the binomial distribution, right? So on average, I will see half of the species, the variance will be 1/4, et cetera, et cetera. Right, so that is a case we can solve. We're done. See you tomorrow. Yes?
You're saying you're sampling the growth rate with a normal distribution with mean 0 and sigma squared, right?
Mm-hmm.
What do you mean by a negative growth rate? Because
A negative growth rate is, for example, if we were to introduce a, you know, like a, I don't know, a vegan in Texas, right? Or like, or something like that, where you cannot find food, then you die, right? That would be the idea, like a consumer, for example. Right, so you can think of like either things that are lacking important resources that they need to grow, they will die. For example, a consumer without their resources, or like some resource, like plant lacking, I don't know, nitrogen, because there's no nitrogen in the system or whatnot. All right, so in this trivial case, It's very nice because we can, without doing any math, we can say this has to be the binomial distribution, right? Because we're just sampling. So the next step we're going to do is to simulate this process and then see what we get out. So this first part of the code is exactly what we had yesterday. So let me just copy this and paste it into R so that we're ready to do our assembly. And while it's doing that, I'll explain a little more about the code for like building a random matrix that is this table, and then doing this process of assembly. So first, how do we build a random matrix and make it stable? What we do is very simple. Like, imagine that we start with an empty matrix, that's this line here. And then, because we only care about the upper triangular part of the matrix, because then we're going to copy it over in the lower triangular part, I just sample and choose 2 values for the upper triangular part. And notice that I also sample these from, let me write it here. Aij comes also from a normal distribution with mean 0 and variance whatever you want, sigma Aij squared. Then I copy this over into the lower triangular part, which I can do by summing to its transpose. And so now we have a symmetric random matrix. The problem is, how do we make this stable? And to make this stable, the simplest way to do is to just put some sort of constant on the diagonal that makes it stable. So we compute the eigenvalues of this matrix, take the largest, and make the diagonal negative as slightly larger than that. I put like that plus 0.01, right? So it's barely stable. Right, so that's how we define, for example, these type of matrices. And now we can copy these. Then paste. And then what we can do is to take some sort of like random system. Imagine I take a system with 7 species. I take a random matrix that is stable and symmetric. I take random growth rates. And then I start at some initial condition and then just integrate the dynamics. So if I do this, we will see that some species survive. In fact, 5 species in this case should survive. So this is my plot. We can see there's 5 species that survive and 2 that go extinct. Species 3 and 7 go extinct and all the other ones survive. Right? So in this case, we had started with some system. We integrated dynamics, and so this thing would be 5 species at the top that are all the species besides 3 and 7 would be the resident community in the equilibrium, and then this would be 0, would be the other 2 species. All right, and then just to show you that this is actually like that, what we could do, or notice that this is like our equilibrium. Just to say, is this due to initial conditions? And I want to show you that in these type of matrices that we're studying, initial conditions don't matter very much as long as they're positive. I'm going to repeat this. You don't have to do this on your computer. We're just like setting species 3 and 5 that are the ones that go extinct to a very large number. And what happens is that they still go extinct, right? So nothing much changes. In fact, you can actually show, like as we just did, that this has to be a globally stable attractor. All right? Now, do we really, yes?
So in trying to build a random matrix that's stable, the way you did it was you picked a random matrix and you said, okay, of course it's not stable, so let me fix it by putting something on the diagonal.
Yes.
The other way you could have done it would have been to say, I'm going to choose out of a distribution and I'm going to constrain the distribution. The
yes.
law is Gaussian, and then in some sense you edit, only allow the things which
right.
which are stable.
Absolutely, yes. This is just like...
Both have different distributions of eigenvalues, don't they?
Yes, but like for now, for these results to hold, all we care about is this matrix negative definite? If it is, which means like if it's symmetric, it's a stable matrix. If it is, all the figs are the same. But for the derivation, actually, this will turn out to be very convenient to say we have off diagonal that come from a distribution center that's 0 because that I need for my proof later on. What I wanted to stress is like, do we really need to waste electricity integrating differential equations for a system like this? And the answer is no, we do not, right? So this is like very convenient because we can actually find a very smart algorithm that actually was originated in game theory, which we're going to talk about tomorrow. It's called the Lemke-Hosson algorithm that you can adapt. I mean, you can adapt, if you're my student, Carlos Servan, that is like the person that did most of this work, and is very clever, like you can use this to just solve for the saturated equilibrium point without having to integrate the dynamics. And because this is a little more involved, I've coded this up and you can load it like this, but I just want to show you how to use this code. So if I load this, that is on the internet, now, you know, I have this function that says get final composition. You put in like a matrix and a vector of growth rates, and what it spits out is like the density of the saturated equilibrium. So you can see here again, the species 1, 2, 4, 6, and 7, they coexisted, some sort of positive number, and the other one go extinct, and they are 0. All right, so this is like much faster than integrating the dynamics, which is good because now we want to do this a bunch of times. All right, so the experiment, the numerical experiment that we want to do is what I call the random zoo. And the idea is like that you go into a large city that has a large zoo, and then you fence off the zoo, open all the cages, and come back after 50 years. Right? So you can imagine these species have never seen each other. They're basically having random interactions because here you have a penguin with a lion, with like a kakatoa, and whatever else, right? So like these species are just like random species from the world that we happen to like for some reason or another. And so they will establish their interactions, and eventually some will go extinct and some will thrive in the zoo, right? Or another way to think about this is I take all of the species in my meta community and I just throw them all together in the island, right? So it's an invasion where all the species invade at the same time. It doesn't matter which number they are, but imagine, yeah, with the same number for simplicity. Okay, so this is the process. We take all the species and we just shove them all together into the same place and see what happens. So how do we do this numerically? We have to decide how many times do we want to do these random zoo experiments. Here I do it 2,000 times. We need to choose like how many species do we want to have in our pool. Here for simplicity, because my computer goes like with coal, is like a bit old. I chose 5 species. You can, if you have a faster computer, you can put like 20 or whatever you want, right? And so for each draw of this process, what we do is like we build a matrix, we build the growth rates, we get the final composition, we count how many species are persisting. So what is the size of this set K, right? How many species will coexist at equilibrium. And then we just plot the results. Okay, so if we do this, what does this distribution look like? No? We just mentioned it like a minute ago. Otherwise, I wouldn't have gone through this exercise of having you mention the name of the distribution. Binomial, right? It looks like the binomial, does it? So let's like overlay the binomial distribution on top of this. Ta-da! So it's quite surprising. We did this process where we have all these interactions between the species, and what we got out is exactly the same result that we would have had if the species were not to interact at all with each other. Right? So how do we go about explaining this type of result? Right? Is there some argument that we can make and say, is it really true that when I have this process, like under these conditions where this is like normal, this is normal, then the number of species in the finite community is going to be binomially distributed. And so like there is a proof of this in our paper on this stuff, but I'm just going to give you like a gist of it by showing you if it's really like binomial, the probability of having all the species should be what? It's binomial with parameters n and 1/2. So it's going to be 1 over 2 to the n, right? So that's like the probability of having all the species should be fairly small. So if I have 10 species, it's 1 in 1,000. If I have 20 species, 1 in 1,000,000, right? So it grows fairly quickly, right? The number at the bottom. So like, let's see how we can do that. And let's also check the time that I don't want to be too late. So what we're saying is, like, what is the probability that we take a system and this vector here, x bar, it's all filled. So it's really x star. It's like all the species coexist happily with each other when we throw them all together. So what we want to compute is like the probability that x star, which is minus a minus 1 r, is all greater than 0. And what I want to show is that under this condition, it's with probability 1 over 2 to the n. Okay, so imagine that we have an A that is invertible, otherwise we cannot do this. And then we have like this equation, and imagine that we're just taking minus A minus 1 r, and then we just compute this vector. This is going to be a vector. If all of the signs of this vector are positive, we have like a coexistence. If not, we will have a certain pattern of sign, right? So some of them will be positive, some of them will be negative. And so what I want to show you is a process in which we can flip the sign of one of these components from negative to positive or vice versa. And the way we're going to do this is by defining a matrix, a diagonal matrix, dk, which is just like minus 1, delta, this is Dirac delta ik, Dirac delta ij. So for the physicists, they will like this notation. For the other people in the room, including me, this is basically the identity matrix, right? So I have 1 everywhere, besides in position k, where I have minus 1, right? So, and then there's zeros elsewhere. Okay, is this clear how this matrix is built? Now, what happens is, if I take this matrix, dk a dk, and then x star is equal to minus dk of r. So if I flip a sign here and here, right, what I get is exactly the same that I had before. Just let me show you an example because it's easier to see an example than to discuss it. So for example, here we have an equilibrium that is not feasible. So imagine that we have our random matrix here, we have our random growth rates here, and then we solve the linear system, and we find that this linear system has 2 components that are positive, which is what we want, but then there's a third component that is negative. And so what we would like to do is to flip the sign of this component. So now if we solve, instead of solving the system, we solve the system in which we use this matrix with the first element, minus 1. And so we do d, a, dk, right? So d1, a, d1, and then minus d1, r. What you see is that now we basically have exactly the same equilibrium, but with the sign flipped. Okay, so this is how we can flip the sign of one of these elements. So far, so good? If you have questions, please ask questions. All right. Now, what is interesting is, what is the distribution of this matrix, for example, or what is the distribution of this vector? Because we have this symmetry assumption, like about 0, then the distribution of this is exactly the same distribution as that of A. And the distribution of this is exactly the same distribution as that of R. Right? So we can think of our process of having chosen an R. We could either have chosen an R, or we could have chosen R that is pre-multiplied by all these dk matrices. Right? So imagine that we're choosing an R by saying we have some sort of base R that we start with, and then this is also multiplied by d1, d2, dn, right? And similarly, we would have said we've chosen like our matrix A, or we've chosen like, so this is my new R, right? The one that I actually see is actually coming from this process. Or we could have said this is like multiplied right and left by d1, and then by d2, and then etc. by dn, and then by dn, right? And this is my new A. Okay, so now we want to choose, like, imagine that we can set each one of these matrices, we can either use the minus 1 or not, right? So imagine that now I take this and I either take this matrix to be there or not. Imagine I raise D2. Or otherwise, I could say I set this element K either to 1 or to -1, right? I have two choices, right? So having feasibility in the system amounts to what? To having chosen the right places to put the -1s, right? So for any initial choice, I could choose the right sequence of 1s and -1s such that this is now feasible. And how many choices do I have? Well, I have n things. Each one can be up or down, say -1 or 1. Then I have 2 to the n choices, right? And they're all equally probable because these are like the same distributions, and as such, the probability of having these positive is exactly 1 over 2 to the n. All right, so this is like the gist of this proof that we have. And then, of course, like this is not sufficient, right? Because we want also to show that for all the other cases, you have like a certain number coexisting and the other ones cannot invade. Turns out that you can do the same type of trick for the invisibility criterion, and by doing that, you can prove this in full generality. But so this is kind of, the first time I saw it, I was actually fairly excited because it's saying this process with random coefficient works in exactly the same way as a process in which all the coefficients are 0. Okay, I think we should take stock of these facts for a second. And then like the next obvious question is, what happens if I violate these assumptions, right? So what if all these matrices are not centered at 0, all these vectors are not centered at zeros? What happens is that it gets very complicated to do the calculations, right? So we had a person like in the lab, like Jose Capitan, that is in Madrid, who loves integrals. And he and Jakob actually here spent like weeks and weeks like filling these boards with these integrals, and then every day they would come, a coffee break, we would say, we cracked this, now we have it. And then the next day they were like, we were wrong. And then do it again, and eventually converged. So that's to their glory. They were able to do this calculation. But basically, the gist is the same, right? Instead of having a proportion of 1/2, you get a different proportion that depends on how do you choose these parameters. But by and large, the more you put in, the more you get out. The less you put in, the less you get out. Which is somewhat counterintuitive, if you think. Like, I think if you were to poll the ecologist in the room, you would think, at some point, I put so much that I always going to see the same number of species, because this is the number of niches or things like that. But thinking of random matrices, you're basically implicitly thinking of infinitely many niches. All right, so now we're going to do this a little more complicated, right? Because here we did the random zoo in which we took all the species and just throw them all together at once. And now we want to actually simulate the real process of assembly, right, in which I put one species, wait for the dynamics to elapse, put another species, and then put another species and put another species. So this, you can imagine, like computation is a little more involved. But what we really need is a function like the one that I have on the board that says assembly one step, right? So we start with the bare ground, and then we assemble one step, and then we repeat this process over and over and over, and then we build a larger and larger community potentially, right? And so what we can say is like we have a resident community, and then we have an invader, right? So we choose like the invader. And what I'm going to do is just to write the parameters for the whole pool of species. So we have a pool of species. We already know all the parameters for all of them, right? So we have this gigantic matrix A with all the species in the pool and their relationship with each other. I have a very long vector R of growth rate of all the species in the pool so that I don't have to go and find a new species every time. And so I'm just saying every so often a species from the mainland can come to the island, and this is my invader. And I choose it at random, right? So that's like what the sample 1 to n1 is, just say, take one random species out of the n that are in the pool, and then say this invades initially with very low abundance, and then check which species are present at this time, right? So these would be all the species that were there plus the invader. And then we can use this Lemke-Hoskin algorithm to find like what is the final composition only for the species that are present. And then we just return the new community. So if we reiterate this a bunch of times, we try like to invade with a new species, it attaches to the community or not, or it sends some other species extinct. And we can repeat this and over and over. So let me try just this process, and then we can comment on what's going on here. So these are like the functions that we need. And now I'm going to start a system where there's a pool of 10 species. I build the matrix, I build the vector, start with 0 species. All of them are absent initially. And then I start for like 40 potential invasions, right? So I try to invade the system 40 times, and we have only 10 species, so each one on average gets 4 chances at invading. And then I just keep track of like the total richness of the system, how many species are in the island at any point in time, and of the composition of the system, which species are there. So this is like the code to do this type of stuff. And this is like our assembly path, right? So let me guide you through this thing. On the y-axis, we're just tracking how many species are in the island, initially 0. And then this is like the invasion number, right? So at 0, we have 0 species. Then 1 species comes in. Turns out this species has a negative growth rate at that point, so it dies. So we're still at 0, right? The second species comes in, but also the second species has negative growth rate, and so it dies. And then finally, at the third attempt, species 2 has a positive growth rate in isolation, so it can grow to its carrying capacity. So now we have an island with only species 2. And then you see that immediately after species 1 arrives and can invade species 2, and they coexist. Nice. So they go on like for a while, resisting some invasions from other species until species 9 comes in and kicks out species 1. Right? This is the 2, 9 here. And then species 10 attaches to this community of 2 and 9. And then you can imagine, it goes, they resist a few invasions, but then 8 comes in and kicks out 10, and then you go up, 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 up. And then you get to this state in which you have 8 species out of 10. And then finally, this species 1 invades again. Species 1 that we had seen over there comes back in and kicks out some other species, so our final community has 7 species. Okay? So this is like a historical depending on which species do I try to invade which, I could end up with like a different path in this assembly graph, right? But is this clear? So this is just like the summary of the history. This you can think of time, and this is the state of the community. Are there questions on this? Because now we're going to do it again, and you should notice the difference between the two. Question? Right, isn't that great? Here, like 9 would be like species 1, but then it reverses because the conditions are different, right? So this is like what makes this process a little challenging to study, is that it's not sufficient to look at all the pairs, right? We really need to know what is the state of all the, to the end, possible communities, right? To really be able to do what you want to do. All right, so here we had history developing under our own eyes. The good news about computers is that now we can repeat history again, right? And just like run this process again. So we go back in time and now forward in time, but in a different universe, right? In which there's not the same sequence of extinction and invasions happened. And so we do like an alternative universe. And what happens here is that you can see that the history is different. Now, immediately species 4 comes in, and it can invade, and then resist a few invasions. Then we get 4, 10, 3, 4, 10, 3, 4, 9, 10. We tend to go up for a while, right, without really extinction besides the invader. And then we get to the 8 species community, and then we go back to the same exact 7 species community we had before. Is this the saturated equilibrium, right, with the 7 species being resident and all the other ones that cannot invade, right? And so, turns out, and this is actually an unpublished result, that if we take these type of systems in which we have a matrix that is symmetric, stable, growth rate however you prefer, and then we do this assembly, we always end up in the same point, which is always the same. So there's a globally attractive system, which is to say what? The way I tend to think about this, and this I think would be the centerpiece of like this paper, would be imagine a network, right, where we start with the bare ground, right, and this network could have arrows pointing to all the species that can live by themselves, right, and maybe species 4 cannot live by itself, but species 5 can, right, so these would be all the possible initial steps of the assembly, right, and then, maybe 1 can displace 2, so they cannot coexist, but then 1 and 3 maybe can coexist, right? And then, I don't know, 3 and 5 can coexist, et cetera, and then maybe when we're here, 1 can invade, right? So we could have this thing, and it goes like 1, 3, and 5. Okay, so imagine that this is the graph. This is what we call the assembly graph. And saying that all the histories will go to the same point means what? Means 2 things. First, that this is a directed acyclic graph, right? That we cannot get stuck in some sort of, day of the groundhog day type of thing where we repeat the same sequence of states over and over again. And second, that this directed acyclic graph has a single sink, right? And this single sink is the non-invisible saturated equilibrium. Right, this is still unpublished, but I think Carlos should have a draft by the end of the week, so maybe I can show you something soon. Okay, other questions on this part? So these are the most idealized condition for assembly, something that they call assembly without tears, right? It's the assembly without all the problems of assembly. And here we can actually do some math, and we can show things like that. That, for example, here, history is completely washed out, right? If I were to look at this island after a sufficiently long time, and I repeat history many, many, many times, I would always say the same island, right? So there's no way to infer how did this assemble in time, because I always go to the same place.
Stefan?
Yes?
Do you have an idea what happens when you insert also the antisymmetric part of the matrix?
So say it again.
I mean, if you don't consider just a stable symmetric matrix, but you put also the antisymmetric part,
Yes.
and you consider also cycles on this stuff, do you have an idea what happens?
Yes, yes, so the question is, this is very nice, right? Thank you, Matteo, for not saying that, but I say to myself. But, this symmetry bothers me. That's what Matteo is saying. What if I also include some non-symmetric metrics? And so in the random zoo paper, the one that is cited there, we're actually doing this under some more general condition. So what we're saying is it's any matrix stable, that is symmetric or non-symmetric, but that is Lyapunov diagonally stable, right? So it's the same condition that we have here that we've seen so many times, right? That this is a strong form of stability of this matrix. So it can be non-symmetric, but in that case, this assembly can have cycles. And in fact, we show, in the appendix of the paper, if you look at the last graph of the last page of the 100 pages of supplement that typically accompany my papers because I like to write, there's a graph exactly of this. But, and this is the interesting part, and I don't think I will be able to prove this in my lifetime, we see that asymptotically, this probability of seeing the cycle goes to 0. So if it's large enough, it seems to behave like this case, but this is just numerics. We don't have really an argument for that. In general, anything can happen. Yes?
So what are the simplest things I can add to this to get multi-stability?
Right. So it depends on what you mean by multi-stability. Because Lotka-Volterra, I cannot have, say, this state 1, 3, and 5 at 2 different levels of densities because that would violate Lotka-Volterra. Right, what you would like to do is this, something like that, right? That these are alternative communities that you can end up with. So to have this, you have to have non-symmetry and non-stability. If it's unstable, then it will have multiplicity of these things. How many? Did you count how many, Jacopo? It's exponential in number of species. No one really knows what the exponent is, though, but never mind, but it's more than 1.
And also if you change the response function, for instance, if you type 2 or this.
I would never do that.
But that could change everything.
Oh, yeah. Don't ask me to do it. I'm sure, yeah. Other questions on this part? No? So can we take the 5-minute break, and then we're going to look at something fun just to conclude the class.
So yeah, we'll take a short break and then we'll resume in 10 minutes. Coffee break is after 10:40.